Good afternoon, everyone. I'm Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And first, I want to thank you all for attending and supporting today's webinar, which is entitled Quantum Science 101, presented by the brilliant Dr. Paul Lopata. This webinar is part of our Tech Thursday series, where we'll be distilling complex technologies into introductory webinars on the science and defense implications. So intended for the well-educated layman who want to learn something more about an emerging technology topic area. Let me start with a few administrative remarks. First, all attendee lines are muted. If you do have a question during the webinar, you can submit that question into the question box in the webinar panel that's on the right of your screen. We'll do our best to get through all the questions during the question and answer. No promises, but we will try. We are recording today's webinar for NDIA, WID, and NTSA members who are unable to attend in real time, and for any member who wishes to review the material at a later date. And please be aware that this is being recorded. And then within the next few days, we'll post the recording, slides, and answers to the question and answers to NDIA Connect for your review. Please remember, as always, our goal here is to educate our NDIA membership and to introduce new topics. We're not selling any programs, we're not pushing any policies, we're not supporting any individual company product.
Mark, you just went mute.
Yes, he did.
Hey, Mark, can you hear me?
Unfortunately, Mark lost audio. Paul, if you just want to get started, and hopefully Mark's audio will come.
Okay, great. I will.
Can you hear me?
Yes.
All right, great. All right, emerging technologies are still emerging. All right, so let me start that over again. We're joined by Paul Lopata, recognized leader in the fields of quantum technology and cybersecurity. Paul recently served as the inaugural principal director for quantum science in the Office of the Undersecretary of Defense for Research and Engineering, where I had the pleasure and the privilege of working with him. He led the DoD's extensive modernization efforts in quantum information science. Paul's had an enduring professional commitment to develop quantum technologies with an eye towards practical advantages. Among his key accomplishments during his service at the Pentagon was standing up the DoD Next Generation Atomic Clock program. This is an effort spearheaded by the Office of Naval Research and addresses future gaps in field of DoD timekeeping in contested environments. He served as the Associate Director for Cyber Technologies in the Office of Secretary of Defense, where he coordinated cybersecurity research across the entire department. Paul also worked closely with partners across the federal government, represented the Office of the Secretary of Defense at the SCORE Interagency Cyber Research Committee and the Cybersecurity and Information Assurance Interagency Working Groups. Prior to that, Paul was a researcher and a program manager at the NSA's Laboratory for Physical Sciences, focusing primarily on quantum computing research. He managed a multi-year international research effort advancing the fundamentals of quantum computing technology. And then earlier career roles included consulting at Booz Allen Hamilton in support of cutting-edge government research programs at DARPA and IARPA, and a National Research Council fellowship at the Army Research Lab, where he investigated the effectiveness of quantum sensors. Paul served as the Executive Secretary in the Defense Science Board's Quantum Technology Task Force and on several technical advisory boards across the DoD. His PhD is in mathematical physics from the University of Illinois at Chicago, and his undergraduate degree is a Bachelor of Engineering from Stevens Institute of Technology. And so without further ado, allow me to introduce my very close friend and dear professional colleague, Dr. Paul Lopata, to tell us everything we need to know about quantum science and national defense. Paul, the floor is yours.
Thank you, Mark. I appreciate the introduction. I'm getting a little feedback. Are you? No? Okay. The echo went away, which is good. So yeah, thank you very much. This is a great opportunity to work with you again, Mark, on this lunchtime webinar, at least here on the East Coast, and also to talk with folks around the national defense industries about quantum technologies. It's a topic that's near and dear to my heart. I got the opportunity to work at the Pentagon with Mark helping lead the DoD's efforts in this area for a few years, which was a real pleasure and an honor to work with such a great group of folks in the Emerging Technologies office there. And my goal today is to give folks in industry a sense for the technology, what it is, where it's at, why there's interest in this now, and where things are going. So talk about the various programs going on in the DoD and across the government. And so, my goal today is not to bring you all up to speed to be, writing journal articles in the area, but to really introduce it to new folks who may be curious about it, maybe wanting to get engaged more, and hopefully point you towards places to find more. And so that button works. So so I'm gonna give a little bit of a lengthy introduction. When I talk about quantum technologies, I'll give a sense of what they are, why we're hearing about them now, and why this matters to the defense industry. And then, as I said, talk about what's going on in the government, and then sum things up. And so I think I mentioned these goals already, but this really is an introductory introductory talk on this topic. But with a focus really on national defense and specifically the industry's part in the technology development. Hopefully, get a sense for where things are at in its level of development, and where things are going and what we hope to see. And so because quantum technologies most of them are relatively new, I thought about framing this a little for other technologies that were at one point relatively new, and people were wondering how they'd fit into the defense structure. And so I went back and read some nice letters that Ben Franklin wrote, but of course by hand, to this other gentleman who's a Dutch scientist by the name of Ingenhousz, and I'm probably butchered that. But Ingenhousz was living in England at the time in the late 1700s. Ben Franklin was living in Paris at the time, representing the federal government. And there were these new ballooning experiments by the Montgolfier brothers and others. And it was huge excitement there. And, at the time, Ben Franklin had this famous quote that got published in all the papers where, somebody saw it and said, "What good is it?" And then he turned around and said, "Well, what good is a newborn baby?" And, everybody latched onto that and thought it was great. But, Ben Franklin, in his letters to others, largely in England, started thinking about what good it was. And so, of course, he initially talks about surveillance and reconnaissance using these things, which makes a lot of sense, and indeed was used in the Civil War in the U.S. But he also pointed out to Ingenhousz, that Ingenhousz's claim to fame was discovering that photosynthesis resulted in oxygen being emitted by plants. And so Franklin suggested that this may be a way of transporting troops, and suggesting just how wild it would be if 10,000 troops showed up unannounced, in your country, and what the heck would you do then? And so, because these experiments had been done with two men each, he suggested that 5,000 balloons would not cost more than 5 ships of the line, which at this point I don't have my handy reference of how much ships of the lines cost, but early in the days, he was suggesting, oh, these could be used for defense or war advantage. And clearly it didn't turn out that way. We are not transporting many troops via balloons, but early in the process, this is what one of our leading thinkers put forward as what good is it for these balloons for defense. And for those who are interested, our National Archives have a lot of these letters written by Franklin on the topic of ballooning, and they're pretty fascinating. So another topic, which I mentioned the Civil War, an early adoption of something is where the telegraph played an amazing part in logistics of winning a battle, or at least rescuing many troops. And so here in September of 1863, some 90 years later, from Ben Franklin, in the midst of the Civil War, telegraph was being used as a way to transmit information long distances. And here was an example where 23,000 Union troops were sent from Washington to Nashville via rail. It took them 12, it was organized in 2 days once it was identified that Union troops were pinned down in Chattanooga. And after Lincoln and his cabinet and the railroad bosses got together, they said, look, we got to do this. How can we move these troops? Originally, it was suggested it would take 60 days to move all those troops to Chattanooga, and they did it in 12 days. It required them to close all the lines, divert all the other traffic. They put up a bunch of barges across the Ohio River. I guess the rail lines went that far. All the troops got up, walked across the Ohio River on a barge bridge, and then got on another train on the other side. To feed the troops, they had to have meals brought to the stations, and they brought food in that way. But this whole logistics massive feat was enabled by the telegraph. And so it was something that, you know, the US Army didn't have any telegraph capabilities before the war. And, you know, it's an example of how a something related to defense, something related to, you know, winning battles was put in place, probably unexpected, of being able to do this sort of troop movement. And you know, it certainly requires a lot of you know, a lot of work with other things as well. But you know, the telegraph was part of it, which is just a long-winded way of saying, you know, and reminding folks, and something to think about, is that as I'm talking about these quantum technologies and the anticipated applications, that we're likely going to see some of the anticipated applications that are not going to turn out, like the balloons and the moving 10,000 troops, or like the telegraph and enabling massive logistics feats that you know, folks weren't necessarily thinking about beforehand. And so to talk about quantum technologies, to have an abrupt transition, you know, I'm going to really talk about 4 different categories of them today. And these are largely listed in maturity: atomic clocks, quantum sensors, quantum computers, and quantum networks. And now why I call these quantum technologies is because these machines, if you could want to call them, they rely upon manipulating bits or components of them at a scale where the quantum mechanical properties exhibit themselves and provide a benefit. And so, you know, the scientists, physicists, when we talk about all the atoms that make up us and make up all the things that we use, that, you know, at a fundamental level, they behave these by these quantum mechanical properties according to them, and that these properties don't necessarily show themselves in everyday life, but they, you know, you have to, you know, do some pretty fine experiments to get down to see, you know, that you know, the electrons are doing certain things, or atoms are behaving in a certain way according to these properties. But they sort of smear themselves out in real life. But you know, with these various applications, the clocks and the sensors and the computers and the networks, folks have found ways to either do something better or do something new using these quantum mechanical properties. And I'll go that in a little bit of detail. And so what are these quantum mechanical properties? Well, part of it has to do with things that are like fixed and come in chunks. So like when we talk about the charge of an electron or the charge of other, you know, the nucleus and things like this, that, you know, the charges come in chunks and not, you know, fractions of those chunks. Other properties are things like particle wave duality, interference, entanglement, superposition, coherence. And, you know, a lot of these things are, you know, sound fairly exotic, and frankly they are. And, you know, I think this is why, one of the reasons why the, you know, the field is just now getting going, whereas the science was developed in the early part of the 20th century. Whereas, we're only reaching the point where, since the 80s and 90s and early 2000s, folks have looked at these properties and said, oh, instead of viewing them as a bug, let's use them as a feature. And so, there's ways in which these different technologies are interrelated, but each of them does use some of these properties to try to do something better. And I'll talk in some depth about sort of what they're trying to do better and why it would matter for defense. And as I was setting up this, talk, Arun Seraphin asked me, goes, can you go in a little deeper about these quantum mechanical properties and what they are and how they come about, and give folks a little explainer as to something they could take with them if they're new to this. And I said, well, I'll give it a shot. I said I usually avoid trying to give an explainer because oftentimes when people talk about some of these quantum mechanical properties, they sound a lot like mumbo jumbo. Like if you talk about particle wave duality, you may have heard, oh, atoms sometimes behave like particles and sometimes behave like waves. And then you scratch your head and you say, how does that work? And then you say, oh, you've got superposition where sometimes, something's here and there. And, for me, trying to explain this without leaning back on the mathematics is, it's like some combination of right and wrong at the same time. That, you may get, you may capture things that are correct about the problem, but sometimes you give people the wrong impression about, really how it's working. And so for me, when I look to understand these things, I lean heavily on the mathematics. And so that's why I put this equation down here, which is Schrodinger's equation, as sort of a key element of describing the wave mechanics, if you will, of the of quantum physics. And there's not going to be a quiz. I'm not going to ask you to understand all the terms here or remind yourself about partial differential equations or anything like that. But one of the key things is that in quantum mechanics, we describe these objects, whether they're an electron or an atom or a photon of light, and then you say, okay, well, as it's traveling through space, it sort of spreads out and sort of interferes with other things. And you may be familiar with interference experiments from optics, where you separate a beam of light and it takes two different paths and comes back together, and you start to see fringes. And this in the lower right is a fringe pattern that's developed in that some such experiment, and that we found that not only does light behave this way, but also matter behaves this way too, which is really amazing. And so a lot of these things that come up and are built into the theory have these properties that if you're thinking of them abstractly too much and you try to say, oh, what does it feel like to be an electron that travels on two different paths, then you run into real trouble fairly quickly. And so for me, I tend to lean back on the mathematics, and I tend to think heavily about the experiments that have been done and that make an influence. And so here, as a reminder to just mention some of these experiments, that this one in the upper right, it's called the Millikan oil drop experiment. And it was an experiment that was done at the University of Chicago back in the early 1900s. And I really like this experiment because that big canister you can see in the picture, that's sort of on the right-hand side, that's still at the Museum of Science and Industry in Chicago. And I mean, it looks like a real massive honking, metal can. I mean, that's pretty much what it looks like. And just interesting to look at and, really consider that, that not a primitive experiment, but, it's like a robust, industrial age experiment discovered that, that electrons have this unit of charge, and that it turns out that everything else does too. That, if you're collecting charge in the universe, that it's going to be in one of these units, that you can't get half of one of those charges or more multiples. It all has to come in, ones, which is where the quantum part comes about. And then the other experiment, well, this is an experiment. This is a sign from Las Vegas, a neon sign. But this is just one thing that was discovered is if you put neon in a glass tube and you send an electric current through it, then it starts to make these pretty colors, and that the colors aren't sort of the universal rainbow, but just slices of the rainbow. And it's those slices of the rainbow that allow us to understand that the electron can't just orbit anywhere around its nucleus of neon, in this case the outer electrons of neon, but that it has certain orbits it can be in and other orbits it can't be in, and the light that we see coming out of it is when the electron jumps from one to the other and emits a photon of light that has a very specific frequency. And so by looking at the various bands of light, we get insight into how the atom is behaving. And so, of course, people turn it into exciting cowboy signs and things like this. But at the end of the day, it really is a fascinating experiment that really points towards these interesting properties, and in that case, the sort of fixedness of the spectrum. And so, that was my little bit of a background on the physics. But I would encourage you, if you're, the one place to look is, Feynman has a number of lectures. Feynman, 20th century Nobel Prize winning American physicist, youngest guy in the Manhattan Project. He's got a number of papers and lectures and things like this about quantum mechanics and even early quantum computing things. And I find his stuff to be fairly accessible and a good place to look if you're interested in trying to understand sort of that next step before you get deep into the mathematics. So, all right. So now I'm going to go through each of these 4 technologies, give you a sense for defense industry impact, give you a sense for the maturity, and why there's some buzz now. And so the first one and the most mature are atomic clocks. Now, atomic clocks rely upon the fact that the atoms, as I discussed how they shine in discrete lines of light, is folks, when they got access to electronics for radars, said, hey, look, we can interact with these atoms at these frequencies, at these microwave frequencies, and use those fixed energies of the atom as a reference point, and keep track of frequency extremely well. And these atoms are extremely stable in their frequency that they hold, and use that as our pendulum, if you will. And instead of counting swings of a pendulum, we'll count how many oscillations in the frequency of light, or microwaves, if you will, as they're coming off of atoms. And so these have been used to great effect for many, many years. Here I'm showing three different products that are made in the U.S. defense industry from a company called Microchip. You can see the little logo. So this one is, the top one is a workhorse of atomic clocks, and I forget the number, but it, and folks who know clocks will know the model number. And it's something that if you need a clock that works very well, then people get that. There's a smaller one here in the lower left-hand corner, chip scale atomic clock that was a product of many DoD programs, DARPA programs, and such, and that you can go out and buy now for a few $1,000s, and it doesn't work as well as the top one, but it's also very small and works for less than 10 watts or something like this. And so it's folks have been able to employ this in situations where they need something with atomic clock accuracy, but don't have the space or the power. And then the one on the lower right, for scale, I didn't put any scale bars, but you can see from the little wheels, you probably get a sense that this is cabinet size. This is a hydrogen maser clock, and it has much better accuracy over a longer time period. And so this is a mature technology. It continues to improve. The clocks are getting better. There's different nodes of places where the quality goes up. sometimes the size goes down. And for defense industry, we all have a reasonable understanding that timing is an important part of positioning. Timing is an important part of synchronizing sensors, synchronizing comm systems. And so as we see adversaries trying to disrupt our ability to get time, which by and large is distributed via GPS these days, if GPS is disrupted, then we may need to bring time with us into new places. And so, when we talk about resilient timing in contested environments, this is, the biggest target is if somebody disrupts GPS and our inability to synchronize clocks for communications, for network operations, you name it. There's a cybersecurity component of it. There's clever folks who think of fairly clever and dastardly things to do if you get folks' clocks out of synchronization on the network. And so having your own version of time and being able to get those things synchronized so that you're not susceptible to what you could call a timing attack, that's something that is important. And then when we look at precision timing and novel applications, for there I'm thinking of applications that maybe are multi-sensor, maybe are multi-emitter, and that have very, very high frequencies, and that you need to get timing even better than the than the microsecond or the nanosecond rather GPS scale. Now, why is there buzz now? Well, as I mentioned earlier, there's more discussion of contested PNT. There's new versions of atomic clocks that access these optical transitions rather than microwave transitions, which are pretty amazing, and that folks are looking to miniaturize and see if there's opportunity to deploy. And that there's work being done as well on the chip scale to get those lower cost largely, so that we can look at deploying them further, so that they perhaps go from being a multi-$1,000 device to being a multi-$100 device, in which case it's almost a no-brainer to stick them in places as a backup. So that's the discussion of atomic clocks. So the next quantum technology I'll talk about are quantum sensors, and there's a handful of different sensors that folks have looked at employing for quantum sensors, and they broadly fall into two categories. One is position, navigation, and timing. PNT, largely position and navigations, as we just talked about timing. And then the second is ISR, sort of looking for signals and making sense of them. And so on the PNT side, we're talking gyros and accelerometers, sometimes using magnetometers and local maps, or gravitational sensors and local maps to make sense of things. And then for ISR, largely it's on the magnetometer side. Some folks are looking at gravitational sensors, and really understanding how to sample from the environment. Now, this device here, it doesn't look as polished as the other one. Throughout, I tried to get defense industry pictures wherever I could. This is from a small California company called AOSense. That this is a gravimeter where they're using a beam of atoms that are separated, and that since one is closer to the Earth than the other, they experience different gravitational fields, and so that they can look at the difference of behavior when they bring the atoms back together, one of these interference experiments, and really understand the very, very small differences in gravitational field. And so here we're largely talking about very high precision devices. This is the direction that much of the science and some of the early technology development is heading in. And so that extra precision for defense applications is one of the key things. One of the other pieces of it, though, is these devices allow for new manufacturing techniques. So if you think of old school gyroscopes as being made of things that are extremely well machined and spinning like crazy, you could if you're moving on to, say, an atomic beam to do this instead of this sort of spinning machined device, a lot of the effort that goes into the extreme precision of the machining now gets pushed off into, making a vacuum chamber, making a beam of atoms, some lasers you need to interrogate it with, and some photodetectors. And some of the questions now are, with modern techniques, is this a good trade-off? Can we move from these older high precision machining techniques to move it to optics and electronics and that sort of thing? And from what I understand, the jury's still out on that, but that I would anticipate that as we develop further, that's going to be a trend that we move in. And so the buzz, why is there buzz now? Well, we've got some early demonstrations that have happened in academic labs and elsewhere that just show some amazing precision. That's really neat. Some early prototypes from various programs, whether it's DARPA or elsewhere, have shown some neat promise. And folks are looking for novel applications of these, and not just necessarily looking for where to replace a gyroscope with or where to replace a magnetometer with, but are there new things that we can do with these devices? So for example, one thing that these allow you to do, the magnetometers, you might be able to get a vector magnetometer rather than a scalar magnetometer, and like in one sample tell all the directions of the magnetic field, and that may enable a new application. It might not, but whenever you get something new, it like a new baby, you don't know what the new baby will bring. So the third category I'm going to talk about is quantum computing. Here are a couple pictures. The top one is from IBM, and then the bottom is from a company that just got stood up called Quantinuum. That's a combination of what work Honeywell had been working on, and an English company. I believe it's Cambridge Quantum Computing, but I might be getting that wrong. And this is one area that almost always sucks up all the air in the room when people talk about quantum technologies. There's really some excitement about these days. There's some major investments being made by large companies. There has been major investment made by the U.S. government over the years, DoD and others. There's some early machine demonstrations. You can log into the cloud today if you want and play with some of these. And there's a major buzz around it. There's also concern about, as these machines get bigger, the different type of algorithms that they can run. One of the things that we know that might be possible is if they get big enough, they could factor numbers, solve elliptic curves. These are math problems that have a major impact on our current public key cryptography codes these days. And so there are major efforts happening with NIST and others to develop codes that aren't hackable by a quantum computer. But the hope is that these machines can do many other things as well. And so there's a real research push right now to understand, not just how to build the machines, but how to use the machines. And so, it really is in the discovery stage for new algorithms and applications. And the nice thing is some of these early machines are starting to get online, as I mentioned earlier. And so, folks can not just, write out the algorithms on paper, but they can, the early ones play with the machines and see if they work as expected. And so those are anticipated defense industry impacts with these new classes of algorithms that the computer scientists are working on. And then the other piece of it is that I mentioned the post-quantum cryptography and how new codes are being developed. I anticipate this being a big impact to the defense industry, is that as those new codes get developed, and I believe NIST is going to be publishing the first round of winners in 2024, that there's going to be a big update, a big push to get all these all the places where we use public key infrastructure to update it to, likely in a hybrid mode at first, to use existing codes and new codes both, and then ultimately moving off onto the new codes as those get standardized and the old codes get turned off. There's a term I can't think of, but retired maybe? I don't think that's it either. Okay, so that's quantum computing. So the last piece I'm going to talk about is quantum networks. And you may notice in the picture that it's not a defense photograph, that this clearly looks like a science lab. This, I think, out of the University of Chicago. And, there really is, in the science stage, there is a lot of buzz about what China's doing for novel quantum key distribution schemes. A while back, people were speculating about a quantum internet, but really this is in an early stage when it comes to defense applications. The long term, we can imagine parallelizing quantum computing. That if I have a machine in this office and somebody else has a machine in the office next door, that we could use some networking to combine them. There's limitations for distance, just because one of the requirements of doing this is if you're sending your message in a single photon, that's the photon that needs to get where it's going. You can't amplify that single photon, and so it makes it fairly limited now. But there is some excitement about local networks, and also if it's possible to put some quantum sensors together to get an improved benefit. But that this is very much, I think, in the research stage, and I'm pretty excited about it. But I think this is one of those areas where it's more in the speculation of putting 10,000 troops on 5,000 balloons, and we'll see how that turns out. All right, so in summary, I talked about 4 different areas. We have quantum technologies and sort of most mature to least. Talked about atomic clocks and how they are looking to improve and are making an impact today. Talked about quantum sensors and how they're more nearer term, and then quantum computers that have a lot of excitement but are a little bit ways to go before we start seeing people solving practical problems on quantum computers that they wouldn't just choose to do some other way. And then finally quantum networks, which is fairly exciting, but requires some effort to both mature the technology and look at applications. And so before I summarize the whole talk, I wanted to make a few mentions of various government activities that are going on. And so one major thing that's happening at a national level is what's called the National Quantum Initiative. So this is an activity that's led out of a new office in the Office of Science and Technology Policy of the White House. The new office is called the National, the National Quantum Coordination Office. I put their logo on the lower right there. You can go to quantum.gov. They got a great website, and just look at the various things that are happening. There's a lot of things happening in Department of Energy, National Science Foundation, just a little bit with the Department of Commerce, and really, in some ways, catching up to what DoD and our partners in the IC have been up to for a long time. Is really doing fundamental research, pushing this technology, looking at applications, and seeing where it goes. And so, National Quantum Initiative, they have a number of events and have a number of products that they put out, and they're an interesting place to look. Within DARPA, a lot going on broadly in DoD, but DARPA has a lot of these things happening. There's a number of program managers in DSO and I2O and M2O these days. Those are different offices there, or MTO rather. And they have some pretty neat programs. Some focus on sensors, some focus on computing, some focus on clocks, a little bit on networking. The Office of Naval Research has a neat next generation DoD atomic clock program that's underway and rolling. The Army has gotten a low cost chip scale atomic clock program that I mentioned earlier. And all of these, along with in-house efforts at the DoD research labs, along with extramural efforts that the basic science offices have, really speak to a pretty robust DoD effort going on, both pushing the basic science and then looking at, maturing the technology in areas where it's appropriate, like sensors, like clocks. A lot of international coordination going on, both within DoD and led by the White House. And then finally, one of the big things that's happening is, as I mentioned earlier, is this cryptographic modernization. And so, NIST is leading the way with the standards. DHS had put out a paper recently talking about, what needs to be done to update codes and what one can do to prepare for it. And then, within DoD, there's a similar effort happening to update all of our systems to ensure that we're going to be up at the new standards when they're around. And so in summary, my goals were to introduce this technology to a new audience, talk about where there's opportunities for defense industry with quantum technologies, and then talk a little bit, like I just did, about where the U.S. government has things to address some of these challenges. And so hopefully you got a good sense for what quantum technologies are, why we're hearing about them now, and why this matters to the defense industry. So with that, I think we have a good amount of time for questions. And so over to you, Mark.
Great, Paul, thank you so much for that overview. We do have some questions coming in. So let me start. Let's see. So first question is, will the slides be available? Yes, they will. We'll make that available to all participants. First technical question, and I'll read it directly, reads, thinking about computational complexity as a feature rather than a bug, is it possible that NP class problems could be used to encrypt data that utilize entangled pairs to function as their discretely observable encryption key?
Wow, you started off with an easy one, Mark.
Sorry.
So the the short answer is I don't know. I love thinking in this area because I think there's a lot of opportunity for for some really creative thinking using some of these features of quantum mechanics, using some of these features of the communication. There was recently a white paper that NSA put out on the topic of quantum encryption. One of the things I didn't mention much of is quantum key distribution, which is a method that's been proposed to share keys using entanglement. Well, sometimes not entanglement, but at least using quantum communication. And that the NSA white paper essentially said it's not yet ready for prime time. That these existing protocols for quantum key distribution have challenges to them, and that they're not yet up to snuff for protecting national security systems. They say, however, there's a lot of important research that needs to be done, filling in some of the gaps we have, and they pointed out maybe 5 or 6 things that aren't closed yet. And they said, hey, this is a great opportunity for continued research. So my hope is that that folks will take up that challenge and really think creatively about some of the ways to use this for new applications.
Great. While we're waiting for more questions to come in, I've got a list of my own questions. So
yeah,
I want to start up. There are a lot, as you pointed out, there are a lot of myths about quantum, a lot of speculation about what it can do. How far along do you think we actually are in quantum computing? And how many steps do we need to get to an actual practical quantum computer? And then I'll have a follow-on.
Sure. I define a practical quantum computer as, if your hard-nosed boss has a has the option of investing money in a quantum computer to solve a particular problem that you have, whether it's a government mission problem, whether it's a a commercial problem where you're trying to optimize something, whether it's designing an aircraft or making a some sort of investment portfolio, whatever it is, right? So different people have different computing problems. But for me, a practical quantum computer is where you get the accountant involved and you say, all right, we're going to invest in a whole bunch of time on Amazon cloud, or we're going to buy a quantum computer. Which one's going to solve our problem like better? And then it turns out to be the quantum computer, right? So that's just for a preface on what I mean by a practical quantum computer. And I think we're a good ways off. Some folks talk about oh, it's going to be in the next 5 years. I think that's a little wishful thinking. 'Cause people point to the next 5 years, say, oh well, we can't simulate a system that's like 100 qubits, and maybe we'll have a good super solid 100 qubit system in the next 5 years, and so surely there must be some problem that we can solve there. But for me, when I look at what people have discovered so far on the application side, or even just the esoteric math algorithm side, that the scaling tends to get quite a bit bigger. There's a nice website that Stephen Jordan from NIST holds, keeps up, and he keeps track. He's called the Quantum Algorithm Zoo, and he keeps a list there of all the different various quantum algorithms that have been proposed, and how much better they are than standard classical computing algorithms that are often referred to. And that for most cases there, the machines require millions of qubits, and right now we're at the dozens of qubits, and so there's a long way to go. And might there be a breakthrough? I sure hope so, because I mean we're going to require a few breakthroughs to get to 1 million. And so we're likely some ways away, but I think there's a lot of important work to be done between now and then, and that I think the fact that as a people that we've been amazed at what we can do with computing as it is, I think that is going to keep the excitement up about this sort of new class of computing. Though I think folks, depending on which excited salesman they hear from, may be a little upset when it turns out that they're 5 years from now they're not being solving all their problems with a quantum computer. But I'm okay with that, but I think it's important to keep that in mind.
Great. Here's a question about, the question reads, besides quantum cascade lasers and quantum dots, what quantum-based technologies are emerging for light emission or conversion applications?
Yeah, so the one of the things that gets applied in these new optical atomic clocks is an optical component are these oh my goodness, I've gone blank on what it's called. I had it at the tip of my tongue. It's not a diffraction, it's these frequency combs. They call them optical frequency combs. And so this is some technology that is pretty amazing. A Nobel Prize has been awarded for it, and I like to think of it as a way to down convert from optical frequencies to down into the microwave frequencies. And so it's the frequency combs are one example there that is an optical phenomenon that relies upon this sort of quantum behavior and this interference behavior, and that really gives some access from the the optical domain where, it's very hard to process signals there. Maybe others know better than I do. Down into the microwave and the gigahertz range where it's a little easier. So that's what I would say.
Excellent. Okay, let's see, switching gears a little bit. Could you speak a little bit about the impact or potential impact of quantum sensors on nuclear submarines? And how do you think that impacts nuclear deterrent strategy writ large?
Sure. So, nuclear deterrence using, my model that I have of nuclear deterrence, right, is the nuclear triad where submarines play an important part of it. My understanding is that for the Brits, that's their, leg of the stool, right, that they keep the submarines quiet there, and that if there's, all disaster breaks loose, they periscope up and look and say, oh, yep, London's a ruin, and then, bomb the hell out of whoever did it, right? So, that relies upon submarines being silent and not losing that asset when it's needed. Now, there are various ways. My understanding is that where people look for submarines, and one of the areas is audio, and my understanding is that there's no real quantum audio device. Maybe somebody will think it up and that'll be awesome. But when people look at quantum sensors that have an impact on that domain, they're often talking about gravitational sensors or magnetic sensors. Though, it's important to keep in mind the noise environment and everything else involved, that if you're looking for something in those domains, because it's not just when you have an awesome magnetic sensor, if you're just sampling the noise a lot better, then you just get a better noise sample and you're not necessarily finding any more subs. And so I've been fairly you have to kind of look around the literature. Sometimes there was even a paper talking about magnetic or gravitational detection of subs back in the 70s and things like that. So I think with any of these, it requires really rolling up your sleeve and asking yourself, okay, say the sensor gets better, what is it that we gain out of it? And in some cases, it's you gain in signal, and sometimes you just gain in detection of noise. And so I think it's certainly not a slam dunk for these types of sensors, but it's important to really understand where the limitations are and where they're going to go.
Very good. We have a policy question. So we often talk about the AI winter when funding kind of dropped off, and artificial intelligence and other emerging technologies. Gosh, hypersonics has gone through these cycles over the years. So here we've got a question. Are you concerned about a quantum winter where the hype dies down and funding dries up and it allows our adversaries to gain an advantage?
I think it's possible. So that's the first part of the question is, am I concerned about the winter? Yeah, I think the winter is possible, right? There's a huge amount of excitement, especially with computing right now. And then, the question is, might our adversaries gain an advantage? And, for me, if a lot of funding goes away, then, the things that I have in mind are, there'll be, maybe a lot of, equipment that our adversaries might be able to buy on the cheap. There might be a lot of IP available that maybe, some company attached to, a country that doesn't share our worldviews get picked up, and there may be a lot of labor where, folks who would otherwise want to work on, American projects might get, sucked into working on, some foreign project that they're maybe not thrilled with. And so, yeah, I mean, I think for me, those are the things that I could identify as a way in which an adversary might take advantage of the situation. And, you know, frankly, I think there might be ways to, at a policy level, if an administration was so inclined to, you know, to address those. But, you know, those are the things that I, you know, kind of keep in mind when, you know, if I were to you know, worry about them. But, you know, I think they're all very addressable. And, you know, I think you know, I think it's, you know, possible to, you know, have blankets around in case of winter, I guess.
that kind of leads to sort of a follow-on, which is, you know, when you look at the, to the extent that you can, when you look at the state of investments in various quantum technologies around the world, you know, we've got some examples of other technology areas where the United States is at risk of losing the lead. In some cases, it's already lost the lead. What about our peer competitors in the quantum realm?
Sure. Yeah, there was a nice paper that was put out recently by Rand that, you know, tried to look at industrial base and quantum technologies and try to look at metrics that would you know, try to gauge this, right? As, you know, what are some metrics that we could use to evaluate whether there's a, you know, an industrial base in the U.S. that can satisfy our you know, broader you know, broader you know, technical interests. And you know, I think at this point, you know, the U.S. is pretty strong. You know, I think the investments that we see right now, both in from the government and then from the private sector, are pretty robust. But you know, we certainly will have to keep our eyes on those metrics because they may indicate, you know, a shift elsewhere, and you know, that part of that shift may be to a company that's, or a country that's well aligned with our worldview, or maybe it wouldn't be. So it'll be interesting to see, because there, you know, there's certainly a lot of countries, a lot of organizations around the world who are stepping up their investments in this area.
I assume China is one of the ones that you worry the most about.
So yes and no. I mean, I think some aspects of this is you know, perhaps opportunity to build closer ties at a scientific level, right? I mean, if there's a lot of focus on building, you know, the ability to publish research papers and get, you know, sort of better connected to the scientific community, that, you know, may be an avenue for the U.S. to, you know, and other Western countries to you know, spread more Western-like thinking. Maybe that's you know, maybe that's wishful thinking, but yeah, I mean, China certainly is investing heavily in this area, and they've you know, their leadership has made a lot of public statements about, you know, trying to become a you know, a strong scientific you know, scientific country, and use this as an area where they can you know, promote that strength.
Great. I think we've got time for one last question, and this one is actually a technical question. So the question is, how are group and ring theory used in quantum computing?
Our group, I love this mathematics question. So one of the, so there's, I know more about the group theory piece, and you know, you know, there's some interesting, so the short answer is it gets pretty deep. And but you know, there's one approach to quantum computing, which is called topological quantum computing, and there they are looking at some very strange properties that have not yet been confirmed, but have been speculated to exist at the interface between superconductors and semiconductors, and that there might be possible to get these particles that are sort of halfway between fermions and bosons, where fermions are like electrons. If you're filling up, like in chemistry, if you fill up shells to build the periodic table of elements, that only one electron can fit in each shell, or two, and up and a down, and then you got to kind of build them up from there. Whereas bosons are like photons that don't care. All of them could be in the same place all at once. And there is a lot of group theory that's related to trying to explain how you could describe these particles that don't behave either like a boson or a fermion. And so that is one place where I know that group theory comes in a fierce sort of way. And for some others, I'd have to go back and think about it for a bit.
Paul, unfortunately, we have run out of time on today's seminar, but let me first thank you again for giving this overview. I found it incredibly useful, a nice overview, not only of the technology, but obviously applications and some policy discussions. To our audience, let me thank you all for your attendance and for your questions. I want to remind you, we will be posting the recording on NDIA Connect, that's on the NDIA website, as soon as possible. Thank you again for those of you participating for your membership support of NDIA, for NTSA, and for Women in Defense, WID. If you have feedback about this series, including what we're doing right, what you'd like to see us do better, and especially topics that you would like to see us cover, please email us at eti@ndia.org. And with that, I'll call the session to a close. Again, Paul, thank you so much. Audience, thank you so much. Have a great rest of the day.
Thanks, Mark.